Hello. Homework number 8 time. Um, yeah, this should be pretty quick. The first set of questions here is about matching the various sequences that we had. So we're going all the way back to chapter 10.1. So these are just sequences. We're not adding them up, they're not series. But yeah, we're just looking at the trajectory of the dots as n increases. And yeah, here are the answers that I got. Yeah, this first one, A, is uniformly decreasing, so it seems to match number 18. B is increasing and continues to increase at an increasing rate, so it seemed like 15 was a good option there. Graph C is oscillating, and that makes me think, yeah, number 14 that has the alternating signs of +1 and -1 for every n that you get. Part D seems to match up with 19. That one seems like it's approaching 1 as time goes on. And E alternates but doesn't shrink at all. So E looks like 17. Yeah, that cosine of n pi thing is actually a nice way to get a continuous version of the powers of -1. Anyways, if you were going to make it into a function that had a continuous domain. Anyways, and then F starts off small, gets bigger and bigger, and keeps alternating. So number 16 fits the bill there. A geometric series. Cool. Or, well, sorry. It displays geometric growth. Again, it's not a series. Anyways, moving on. Squeeze theorem, number 70. Yeah. Again, this is just a sequence, and so we bound the sign by 1 and -1 and show that the limit of this thing as n goes to infinity should be 0, because both 1 over n and -1 over n go to 0 as well. Okay, no problem there. Number 25 in section 10.2. Here we have a telescoping series. We need to use partial fraction decomposition to get from here to there. And once you have that partial fraction decomposition, you see that you've got 2 for the first term because our n starts at 0. So 2 is the first term, and then everything else in that infinite sum telescopes, and you're just left with 2 as an answer. Not so bad. Oh, and these are fun. So we've got some, picture proofs of geometric series here. So we have a big old square, and that square is divided into yellow section, green section, purple section, and red section. So that's where we see 1/4 in this picture. Each of the colors represents a quarter of the total area. But if you look carefully about how this is constructed, we can tell that each of the right triangles that we have in this diagram are 30, 60, 90 triangles that have a ratio of 1 to the square root of 3 to 2. You can see, especially, I don't know, like, for instance, on this red part, this section, this hypotenuse is half of the leg above it. Yeah, so we've got a bunch of 30, 60, 90 triangles here, which means that each of these, say these big triangles, have a base of 2 and a height of 1, meaning that they have, I don't know, say an area of 1. And so the big yellow triangle here, the big red triangle, the big purple triangle, and the big green triangle all have the same area as this inner square. So initially what we've done is divide up the big square into 5 equal chunks of area. And so the series that matches up with this, it's a geometric series where, each time we're breaking up the area into 5 equal parts, where 4 of them look like the triangles and 1 looks like the square in the middle. We're breaking up the entire area into 5 equal parts, and so that's the common ratio that we have here in our infinite series, our geometric series, and then we work this out to figure out, oh, hey, in the end, the sum of a bunch of fifths will add up to a quarter of the entire thing. So if we look at the yellows, this big yellow is 1/5 of the entire square, but if you keep taking fifths and adding them all up, you get this entire 1/4 of the area. So that's cool, being able to visualize what happens in a geometric series using pictures. That's fun. So that's number 80. Number 2 in section 10.3. Use the integral test to determine whether the series converges or diverges. And again, we just use the continuous function that matches up with 1 over 3n minus 2. And when you take the antiderivative here, you get a natural log, and that natural log is going to diverge. If I was being good, I would write, the limit as b approaches infinity here. There we go. But yeah, the natural log diverges, even though it diverges slowly. Cool. And then finally, number 34, explain why the integral test is not applicable to test the series for convergence. So remember that the integral test requires that you have a series that is positive, decreasing, and the function that you're using is continuous. Those are all necessary requirements for the integral test because we want the integral to match up really, really nicely and well behaved with the Riemann sum that's representing the infinite series. So yeah, if we look at this one, we've got -1 to the n power over n squared. And if we, tried to use this as kind of our connect the dots function, if we just put in x everywhere where we saw n, this would not even be continuous because of that top part. When you start throwing in fractions and irrational numbers into the power here for x, bad things happen. So that is not a continuous function. You could instead make your kind of connect the dots function this one, and that would be a ratio of 2 continuous functions, and actually would sync up with the original series at all of the values of n. So that would be a better choice for your function defined in terms of x. But even if you use that function, the terms of those series would not all be positive and monotonically decreasing. So again, the integral test wouldn't be great here, but if you wanted to, actually come up with a way to decide that this does converge, you'd use the squeeze theorem, I would say. Again, on top, this thing would be smaller than the series where you just have 1 on top. Then you've got this thing. And then it would definitely be greater than or equal to -1/n². Yeah, so you'd have this kind of relationship going, and you could use the squeeze theorem to prove that that actually does converge when this one converges and this one converges. Yeah. Cool. All right. Well, I think that's it for homework number 8. I will see you in Pronto. If you have any more questions, I'd be happy to help you with any of this or with any of the online homework that you have. All right. I'll see you soon.